Yacoby, I'm sure you can all recognize the links.
So I'd like to start by saying to you, Asa, that you've inspired me in many different ways, certainly in physics, but more importantly, in the way that you balance your passion for physics, your love for nature, and your devotion to your family. And I hope that I could follow in your footsteps, definitely with this kind of balancing act. Happy birthday. So in this talk, I'd like to tell you about some of the recent work we've been doing that explores unconventional superconductivity that emerges at the interface between a conventional superconductor, aluminum for example, and a very conventional semiconductor, one that has strong spin-orbit interaction. And the type of unconventional superconductivity that I'll be telling you about today is one that emerges because of the incompatibility of magnetism and superconductivity. We all know that magnetism favors having spins that are ordered. For example, in a ferromagnet, they're all aligned. Whereas superconductivity in its conventional form prefers having pairs of electrons with opposite spin, opposite momentum, and a uniform wave function, isotropically arranged pair wave function. And these two are really incompatible. And you can ask, well, can these two things basically coexist? And in fact, there aren't that many examples where superconductivity and magnetism coexist. There are really a few, and usually when that appears is when superconductivity is just about to disappear. You might ask why one might be interested in this combination. So one example is that if you can have superconductivity that has, for example, triplet pairing, then you might imagine a situation where you can flow supercurrents that carries spin. This could be interesting from the point of view of spintronic devices where you can, for example, inject spins very efficiently. You might have superconductors that don't care about the presence of strong magnetic fields. And of course, just having some kind of way to tune from one type of superconductivity, singlet to triplet, would be interesting both from a fundamental standpoint but also from applications. Perhaps one of the earliest theoretical considerations of unconventional superconductivity started with the work of Fulda-Farrell and Larkin of Chinnikov. Two independent sets of work came about in 1964 and 65. In the West, this kind of phase that I'll describe is called FFLO. Steve already mentioned that phase in his talk. In the East, it's called LOFF. Basically, different points of view on, these are the initials of these four authors. And what they considered is a very simple situation of a magnet, basically, where you have two Fermi surfaces, one containing spin downs and one containing spin ups. And as you can see, if you try now to create pairs that have opposite momentum and opposite spin, this is not possible. And this pair, for example, has some kind of finite momentum. And what they showed is that this system, under certain conditions, certainly under the presence of very large magnetic fields, this system might choose to condense and choose one particular wave vector for these pairs, and hence it produces an order parameter that is varying in space, and its modulation has to do with this kind of pairing momentum. There are, again, only a very small number of examples of this phase, and even those are believed to be a little bit controversial still. Here I'm showing an example from a organic superconductor where one believes to have this kind of FFLO state existing just before the transition from superconducting state to normal state in the presence of a very large magnetic field. And there have been some other examples that are believed to exist in heavy fermion compounds as well. But a turn of events in this field of trying to realize this kind of FFLO unconventional superconductor came about when one began to consider proximity effect. And as you all know, if you put a superconductor in contact with a normal metal, superconductivity leaks in and has basically its order parameter leaks into the normal metal, leaving pair correlations in the normal metal. And if the superconductor has singlet pairing as outlined here, that order parameter penetrates. And of course, in a system where in the superconductor there is no triplet pairing, then that will of course remain zero also when you consider the proximity effect. But something different happens if you ask what happens when you try to proximatize a metal that has magnetic order in it. And this is in the limit of weak exchange interaction. It turns out that the singlet order parameter begins to oscillate in the ferromagnet. And even more surprising, a triplet pairing amplitude emerges. It was zero in the superconductor and yet starts to oscillate also. And it is out of phase with the singlet order parameter. Namely, when the singlet pairing amplitude vanishes, the triplet pairing amplitude is maximum. And this oscillation and this period is exactly the manifestation of this FFLO state that I described before. What FFLO considered was the bulk superconducting state, and here this is an induced pairing amplitude that takes place in a system that has no intrinsic pairing of its own. The problem, however, is that as you strengthen the ferromagnet, the period of oscillation increases, and also its decay into the ferromagnet becomes shorter, and hence, in the limit of a very strong ferromagnet, you basically end up with no leftover, neither singlet nor triplet superconductivity in the ferromagnet, and you can't really take advantage of this kind of triplet pairing inside the ferromagnet when the exchange interaction becomes too strong. And this has led to a search of how can one actually create a long-distance triplet pairing amplitude that will survive in a system. And the field is basically bifurcated at that point. One direction that the community that still considers superconducting ferromagnetic junctions is considering as one where ferromagnetism is inhomogeneous, namely changing, the direction of magnetization is changing in space, and it turns out that using that kind of ideas one can sustain the triplet pairing amplitude and even equal spin pairing over long distances. And the approach that I'll be taking is one that is different. I'll be considering hybrid devices that consist of these conventional phase magnets and superconductors, but now together with materials that are more of a modern flavor. These are materials that have strong spin-orbit interaction, and as we know, these have led to topological insulators in the limit of two-dimensional quantum spin Hall phenomena. And it turns out that this hybrid kind of geometries between superconductivity and materials with strong spin-orbit interaction has a lot of richness to it. For example, combining a conventional magnet with a topological insulator can lead, together with superconductivity, can lead to basically chiral Majorana modes. Just the presence of magnetism and topological insulators leads to a quantum anomalous Hall effect, which basically has a quantized Hall phase in the absence of an external magnetic field. And closer to what I'll be talking about today is hybrids between conventional superconductors and indeed two-dimensional systems that have strong spin-orbit interaction. And here I'll show that we can generate triplet superconductivity that persists over long distances in the semiconductor, and I won't talk about other type of unconventional superconductivity, the flavors of topological superconductivity that then they themselves can lead to interesting non-abelian excitations. The system that I'll be talking about can host both these kind of phenomena. I'm just going to be talking about how to induce triplet superconductivity based on spin-orbit interaction and the proximity effect. So schematically, the devices that we are working with are shown here. You have a two-dimensional electron gas. We're going to be working primarily in the conduction band where the system has strong spin-orbit interaction. We deposit two superconducting contacts here. These are aluminum contacts for the purpose of this talk, but we've considered other superconductors as well. And we also have a metal gate on top that allows us to tune the density of this semiconductor from its conduction band all the way down close to the gap. And as I mentioned, this material has in the limit where the Fermi energy is in the gap is a quantum spin Hall effect where current is only flowing along the edges. I won't talk about that. I'll mention just one aspect of that. as I go along, but most of the talk will focus on what happens when the Fermi energy is somewhere in the conduction band away from the topological limit and only considering the effect of spin-orbit interaction. So here's a schematic of our device. You see two superconducting contacts going from top to bottom, a small section of this two-dimensional material that allows us to send supercurrent through the proximity effect from one contact to the other. And if you look at the supercurrent as a function of flux, it generates the conventional Fraunhofer pattern where you see, as a function of flux, this kind of oscillating behavior, a large supercurrent that then dies off as 1 over the field, as you'd expect for a geometry where current is flowing uniformly from one contact to the other. The ingredient that we will be adding is to see how these kind of Fraunhofer patterns that are telling us something about superconductivity in this geometry is affected by the presence of an in-plane magnetic field. Now, instead of taking at any value of this magnetic field here, the entire map of critical current versus flux, we're going to just focus on the zero DC current limit, namely looking at the differential resistance of this system, and it's going to give us enough information to understand what superconductivity is doing. And here's one line cut, for example, near zero current, where you see that the resistivity is 0. At 0 flux, this suggests that there is a strong supercurrent flowing, and then the system goes normal at the nodes, and in between the nodes, the differential resistance goes down again. Whether it goes all the way down to 0 or not depends on temperature and depends on the noise in the system. But as long as the resistance here is lower than the normal one, we'll assume that the system favors a superconducting state, and we'll use that as an indication of the presence of superconductivity. And so now we can look at this differential resistance. Here's the color map as a function of parallel field, and you can see that these kind of diminished resistances where the system wants to be superconducting are a little bit lifted. So superconductivity weakens on the nodes here, on the sides, on the lobes, but it remains fairly strong in the middle. And the scale here is half a Tesla. And just to contrast that, note that the scale that we use to generate the Fraunhofer pattern, the interfering flux, is on the scale of millitesla. So the perpendicular flux is very, very weak, and we're not going to consider its effect on the physics. We're only going to consider the effect of the in-plane magnetic field. Yeah?
So what's the distance between the two superconductors?
It's about a micron.
That's a micron.
Yeah. So it's a fairly, very long distance. Yeah. Now, the surprising thing is that if you continue to increase the magnetic field, you see that superconductivity went away, and we don't see any of the nodes anymore. But then as you raise the field further, it comes back. And it's not very strong. I'll show you a little bit of a better example as we go along, but nonetheless, the fact that it disappears here doesn't mean that the superconducting contacts became normal. Clearly, the system has superconductivity left to it, but somehow something killed it in the middle, and that's what I'd like to demonstrate, to explain. And what I'll argue is that exactly at this condition, what happens is that the pairs that are injected from the aluminum, that are singlet pairs, as they propagate from one side to the other, they are fully converted into triplet pairs, and hence cannot enter the other superconductor, and that's the reason that superconductivity, supercurrent, is gone at this particular magnetic field. So this will become clear as I go along. Now, we can create what I call a phase diagram, basically looking at superconductivity in this system, or the Josephson current, as a function of both magnetic fields, so this is what you've seen just now, but also as a function of density in the system as we tune the chemical potential. And we're going to plot here only the zero flux cut. That's the cut that has the strongest supercurrent altogether. And here you see this cut at this particular density, where you see that we have a strong zero, and the superconductivity, it goes away and something comes back. And we can take these Fraunhofer maps at different densities and different magnetic fields to generate this entire map here. And again, this is just differential resistance, but it very clearly shows that there is supercurrent flowing in this blue domain here as a function of diminishing density and increasing magnetic field. But then there are three other pockets in which superconductivity comes back. It goes away along this yellow trajectory, which is the normal resistance. This resistance plot is normalized by the normal resistance, so anytime you see this yellow color, it basically indicates that the system has its normal resistance. And this portion here we know to identify appears at very small or low magnetic fields in the plane, but at very low density. This is the limit of the quantum spin Hall effect. So this is the topological limit where we've tuned the chemical potential into the gap, and this superconductivity has to do with current flowing only along the edges, and I'm not going to talk further about that. What I'd like to focus on are these two pockets here, and I'll show that these two pockets are strongly associated with the presence of triplet superconductivity in this system, and they have quite a different flavor or origin. So I'm going to start by focusing on the high density limit and trying to understand what happens here, which is this particular type of Fraunhofer pattern. And remember, this system has strong spin-orbit interaction, so if we look at the Fermi surface of the system, we know that it has two Fermi surfaces, one containing spins going counterclockwise and the other having spins rotating clockwise, with perfect spin momentum locking on each one of the Fermi surfaces. And we're injecting a singlet from the superconductor, and it's easy to see that we can construct the singlet with this Fermi surface very easily. The up-down component here appears within the inner Fermi surface. We have an up-down. And the down-up of the wave function appears on the outer Fermi surface. And you see that this pairing mechanism is a perfect singlet that has zero net momentum, and the wave function is nicely isotropic in space. But now the interesting thing happens when you turn on a magnetic field. When you ramp up an in-plane magnetic field, it's not hard to see that the Fermi surfaces distort. And the way they distort is that one circle moves to the right, perpendicular to the magnetic field, and one moves to the left. And the reason is very simple. The spins that are perpendicular to this magnetic field on the top and bottom here, they're perpendicular to the magnetic field, their energy is unaffected. And so these momenta are unchanged. The momenta of the spins that are parallel or anti-parallel, they act differently. The ones that are along the field gain energy and hence acquire a shift in momentum, and the ones opposite the field lose energy and therefore they lose momentum. And the difference between these two Fermi surfaces is exactly given by the Zeeman energy divided by the Fermi velocity, and peculiarly enough, does not involve the spin-orbit interaction. So even though to get this kind of effect you need the spin-orbit interaction, the magnitude of the shift is universal. It just depends on the Zeeman energy and the Fermi velocity, and this is in the limit when Zeeman is weak compared to spin-orbit interaction. So in that limit, the details of the spin-orbit interaction do not matter anymore. But now something interesting happens, and that is if you look at this singlet pairing that we have injected, we see that now this pair, the up-down and the down-up, each component acquires a momentum, very much like the FFLO phase. And this momentum now will give a phase factor to this singlet such that at a certain distance, for example, we can convert this singlet to a pure triplet. In fact, one can easily write this kind of wave function as a sum of a cosine times a singlet plus a sine times a triplet. And you see that depending on this distance W, and here I've put in the distance between the two superconducting contacts, for a given delta K, we can reach a situation where the singlet amplitude vanishes entirely and we're only left with a triplet component. Now note, I've plotted here a pair propagating from point x1 to x2 along the direction where the momentum was acquired. But if you consider other trajectories that, of course, add on to give you the total supercurrent in this geometry, note that a trajectory going from x1 to x2 along the diagonal, because the momentum shift is only in one direction, will still acquire the same delta K times W. So it basically tells you that all trajectories from one contact to the other, doesn't matter in which way you look, will all have exactly the same phase factors and will add coherently one to the other. And note that the amplitude here is going to oscillate nicely with magnetic field and is not going to decay with magnetic field as in the case of the superconducting ferromagnetic junctions. One can nicely simulate this in a semi-classical limit This is what you'd expect for the pairing amplitude or the supercurrent as a function of magnetic field with realistic parameters for this particular system. And indeed, you see that roughly at 1 Tesla, the Fraunhofer pattern disappears and reemerges, and this is basically what we are seeing. So this explains this corner here, where I call this spin-orbit dominated, namely spin-orbit is much stronger than Zeeman, and hence spin-orbit does not enter the results. But now let's consider what happens in this corner. It turns out that in this particular area, the Fraunhofer patterns look quite different than the ones that we saw here. Note that in the ones that we see here, we basically are left with nothing at this node, whereas in this particular case, only the central lobe disappeared, but the side lobes remain and they merge inwards. So something else is going on. And it turns out that we can understand that in the limit where now spin-orbit interaction is very weak and we're dominated by Zeeman. So this is actually exactly the case that the FFLO people considered. We have one Fermi surface of one spin species, let's say down, and one Fermi surface of spins pointing upwards. And now if we want to construct our singlet pair, we have to do it between the two Fermi surfaces. The up-down would be an electron on the outer Fermi surface with an electron on the inner one, and the down-up would be the other pair. And again, you see that each component of this pair amplitude of this wave function has a phase, very much like before. The only main difference is that now this momentum shift is isotropic. Note that it doesn't matter in what direction I choose my pair, I get exactly the same delta K. And so now we have a phase that will depend on the length of the trajectory because this pairing momentum is now isotropic, and this will lead to this kind of constructive and destructive interferences as we're summing up all these phases. And if we now construct what the supercurrent or the Fraunhofer pattern will do as a function of the interfering flux, we see exactly this Fraunhofer pattern characteristic of the strong Zeeman limit where the central lobe disappears and the side lobes are merging inwards as we go up and up in field. And just like the SFS case, the superconducting ferromagnetic superconducting case, note that the magnitude of this supercurrent is indeed now diminishing with magnetic field, unlike the spin-orbit dominated case where that amplitude is not decreasing. So within one sample, in fact, you see that we have very interesting pairing amplitudes. We have the spin-orbit dominated, we have Zeeman dominated, and we have the quantum spin-Hall regime. And in fact, theory doesn't tell us why is it that we stop seeing the spin-orbit dominated and cross over to the Zeeman dominated. So there are things that we don't understand in this measurement, but nonetheless we can identify the microscopic origin of the physics very clearly from these Fraunhofer patterns. So before summarizing, I'd just like to comment a few things about the spatial dependence of this order parameter. So we've looked at a given geometry, but in fact one can also make devices with different distances. And it turns out that this order parameter that oscillates in magnetic field also, as you saw, oscillates in the separation between the two contacts. And in the limit where we apply the magnetic field parallel to the contacts, this order parameter is oscillating exactly in this form. And interestingly enough, in the limit of the Zeeman-dominated limit, we get both an oscillation away from the contact, but also away from the boundaries. Now, one thing that I didn't have time to talk about is what happens when we apply the magnetic field in the opposite direction. So far, I've talked about field pointing in the direction parallel to the superconducting contact. What happens when it's acting perpendicular to it? There it turns out that the order parameter is continuously dropping smoothly from the superconductor and away, but oscillates perpendicular to the contacts, to the boundaries. And one interesting aspect of this particular field direction is that if you only had one Fermi surface, as you would have in a surface state of a topological insulator, this kind of interference and oscillating order parameter would survive. So even though the way I described this physics was an interference between the two Fermi surfaces, it turns out that certain components of this physics are directly a manifestation of only one Fermi surface alone, and would survive, for example, if we had only a single Fermi surface. Now lastly, what I'd like to say is that this kind of singlet to triplet converter can be a very interesting mechanism of trying to determine what is the pairing amplitude in unknown superconductors. So imagine, for example, we have our aluminum and we have our semiconductor, and we put a superconductor in which we don't really know what the pairing mechanism is. Is it singlet or is it triplet? In this particular case, you see that if this was a triplet superconductor, then already at zero parallel field, we cannot send any supercurrent through the device. But as we turn on this parallel field, we'll be able to convert those singlets to triplets and get a maximum supercurrent. So this Fraunhofer pattern will be a way to directly tell us what is the underlying pairing mechanism in this system. So with this, I'd like to summarize by acknowledging another triplet pairing. And these are these three students, Sean, Hetchen, and Michael, that have done this work. We've also benefited from strong collaboration with Bert Halpern on the theory, and Lawrence Mollenkamp and his group for the work on the mercury telluride samples. Thank you.
Questions?
So you had data. I wasn't sure if it was data or illustration of data to come, the oscillations.
So I did not show it. We have, we don't have a continuous set of distances to show an oscillation. But in fact, something nice that we've done was to create an interferometer that has two distances, one very short and one very large. Because one interesting thing is that even though after you get, this max, note, beyond this node here, you again recover a singlet pairing, but it has the opposite sign. So if you have a junction of a narrow junction, a large junction, what will happen is that you can convert one junction to a pi junction, and the other one will remain a zero junction, and you can very clearly see that interference. So the spatial nature, we've demonstrated that by looking at these kind of interferometers that have different sizes.
So do you really know that this is a triplet? Okay, you do see that the singlet sort of oscillates, and it's something else.
Yep. The way we understand things in physics is by comparing it to various models, and we have consistency, and we have many aspects that are consistent in this measurement. The fact that, for example, when you replace the superconductor with a different one, you change the length, you can change the G factor. In fact, in these systems, as you tune the density down, what you find is that the G factor is changing, and that should affect the Zeeman versus Fermi velocity ratio. So there are many things that are consistent with this picture, and hence our conclusion that that's what's going on. We don't have a direct tripleometer.
You have these two pockets of different gate voltages. So in terms of band structure, what's the differences between these two gate voltages? Fermi velocity, what's the main?
Well, Fermi velocity, as far as we know in this system, is actually quite constant. It's nearly a Dirac system all the way down to very low density. So I don't believe that that's the case. What's not included in this theory, in this very simple theory, is the canting of the spins. So in the limit where I mentioned, Zeeman is much weaker than spin orbit, I'm basically assuming that I'm only shifting the Fermi surface, but spins are not canting at all. It might be that what's happening is that the canting is important, but we really don't know. We don't have an understanding of why the system crosses over from one behavior to another.
Okay, so let's thank Amir again.